This is OPTI 380A, Lab 10, Semiconductor Light Sources. I'm Zeller.
I'm Sophia Centeno.
And I'm Ethan Luker.
And our TA is Liaf. In Part A, we examined an LED and a laser diode, LD, under a digital microscope using Thorlab's imaging software. After calibrating the microscope with a ruler, we determined how many pixels equaled 1 millimeter to size each device accurately. By adjusting the drive current, we viewed the red, green, and blue emitters of a variable LED, each with an area of about 0.5 millimeters squared, or half the expected area. The LD cavity measured 1.94 millimeters, within roughly 21% error of the datasheet value. From this cavity length, we calculated a mode spacing of 0.033 nanometers, smaller than the expected value of 0.3 nanometers. This part showed how microscopic structure and drive current influence LED and LD behavior. In Part B, we used an optical spectrum analyzer and logger probe to record spectra for the LD and LED. As we increased the LD current, its output evolved from noisy subthreshold emission to a clear peak at 20.87 milliamps, marking the lasing threshold. The mode spacing appeared with a distance of 2.53 nanometers. Above 21 milliamps, peaks appeared about 2.84 nanometers apart, larger than the 0.033 nanometer from Part A, likely due to measurement error in estimating the LD cavity length. The LED spectrum showed a broad red peak consistent with the reference data. Overall, this experiment illustrated how current drives lasing and contrasted the narrow spectrum of a laser with the broad output of an LED.
Part C. We looked at how the light spreads out from both sources and how each one behaves when viewed through a polarizer. The LED gives off light in many directions from a larger area, while the laser diode gives off light in a much tighter beam mostly lined up in one direction. We connected each source to a function generator and aimed it at a photodiode hooked to an oscilloscope. We rotated each source degrees at a time and recorded how the signal changed with angle. Then we placed a polarizer in front of the detector and rotated it to see how the brightness changed. The LED light pattern spreads power over a large range of angles, which shows that it isn't very focused or strongly polarized. The laser diode showed a narrow peak around the center, which means its beam stays concentrated and is highly polarized. The laser diode showed up at a higher P ratio than the LED since its light is strongly aligned with one direction. This did not align with the theory, and potential errors could have come from inaccurately collecting signal values when inserting a linear polarizer into our system.
This is Part D, power output versus drive current for a laser diode and LED. In this experiment, we study how optical power changes with the drive current for an LED and a laser diode. The setup used a DC power supply or laser diode driver connected through a multimeter to measure current in an integrating sphere with the photodiode amplifier to measure output power while blocking straight light. For both the LED and the laser diode, we split current from 0 to 40 milliamps in 4 milliamp steps, measuring the power alongside it. The plotted curves of power versus current are shown on this slide, each with a relatively low error. Overall, our results confirm that the LEDs emit proportionally to current, while laser diodes exhibit a distinct lasing threshold where optical gain exceeds losses. Across the full lab, we demonstrate how physical structure, spectrum, divergence, polarization, and power behavior all differentiate LEDs from laser diodes, linking their optical properties directly to the design.